All right, so hello everybody. Yes, so I'll say a bit about the motivation for this talk. So I was worked at this company Contextual, and we had some junior engineers, and every week somebody would run up to me and say, "Hey, Yaroslav, we should do this. This paper says this totally works." And I actually was pretty sure it doesn't work. So I wanted to give a talk, and I gave it at the company first to encourage some healthy skepticism in published results. So one concrete thing I realized, I have this paper file library I use to track papers. And right now there's more than 2,000 papers that I've saved and took notes on. So it's like 2 papers per week for the last 20 years. And the vast majority of them are, not really practical. Some of the papers are, foundational. You have convolutional networks, backdrop. Somebody's typing. Can you mute? So some of them are really foundational, like we have convolutional networks, backprop, transformer. Let's see, I don't know how to put them there. But many of them are not very useful. And right now there's a big explosion of papers. So if you search for machine learning in Google Scholar, you see that last year there were 100,000 papers mentioning the words machine learning. So essentially, the picture looks like this. So you have, this orange stuff. This is the stuff that's practical, that works. There is this published papers, which is blue. And, somewhere there is intersection. And if you zoom in really far, if you have a very high resolution screen, you'll see like a little green pixel in there. So this is the intersection of papers which are both published and practical. And the interesting question to answer is, why is this intersection so small? So first of all, I don't think the intersection is 0. And there is examples which are obviously working. Like right now, I use Waymo almost every day. That's obviously using machine learning, and it works. But let me give you an example of something that doesn't work. So, there's this. The bigger question is, you have this huge number of papers and they're not practical. So what are those papers? Where do they come from? Like, why do they exist? So here's like one specific example, just a random example from long ago, so we don't, upset the original author. So back, 15 years ago, this field, belief propagation, was very hot. It started because people noticed that some practical task like error decoding was solved by belief propagation, and that got people excited, but then they kind of weared off and they forgot the original task, and they started just studying belief propagation for the sake of it. And you have papers like this, which takes belief propagation, derives some formulas, has an improvement. One thing, so there's usually some graphs, so you see as you increase the computational complexity, the error also decreases. One thing this paper conveniently forgets to note is that the time grows exponentially with this. So this method is completely impractical, but you don't have to reveal that. So this is like just a random example of a paper which is published but not practical. So to summarize, this paper takes some application which, on synthetic examples, it's solve the problem, which is not really a problem, and it's not practical because it's very expensive. So back to the talk. Okay, so yeah, I gave some examples. Okay, so I'll spend the next 5 minutes just giving some background about myself to give some context. So first of all, I was born in St. Petersburg in 1980. My parents were quantum physicists. My dad was quantum physicist. My mom was solid state. In 91, USSR fell apart, and my parents started thinking about leaving because there was inflation. At one point, my parents were paid an actual soap by the university. So the university didn't receive enough money for payroll, but they had a contract with Procter & Gamble, and somehow they ended up with a whole bunch of imported soap. So my parents left. I moved to London. And then 2 years later, I moved to Oregon State. So Oregon State is actually a top-tier school in forestry. So it's the second best school in forest sciences, second only the Swedish University of Agricultural Scientists, agricultural science. And that was actually my first summer job. I was a assistant forest surveyor. So I was like this guy walking around the forest, measuring trees. But in addition to forestry department, it had a computer science department. So I took a computational geometry course. I really liked it. I started a PhD with an advisor who was in computational geometry. We published a paper. Then halfway through, my advisor started to have doubts about his career choice, and he left to India. He invited me to attend his wedding, half a year later, but I was a poor grad student, I couldn't go. So then I got a new advisor, Thomas Dietrich. So he's actually active on Twitter, former president of AAAI. So Thomas Dietrich was very experienced. He was very well respected. So he was the kind of professor who could be on a grant committee to design a grant and then proceed to receive it himself. And normally people would say, wait, can you do this? But in this case, they would say, oh, this is Thomas Dietrich. He can do it. For him, it's fine. So this grant transfer learning was obtained this way. And that's what funded part of my PhD studies. So the first thing that Thomas did, he sent me to a machine learning summer school. So in Canberra, so that was a transformational experience. So going to that summer school, that kind of started me on my habit of reading 2 papers per day, and what got me to where I'm here. So that was an interesting time in machine learning. That's when we actually had a theory of machine learning. So that's when you could come up, do some math, and you say, hey, I can prove this method works. And then you try it out. And if it doesn't work, you have a bug in your code. It's kind of a nice time compared to now where we don't have any theory. So if your thing doesn't work, you don't know if you have a bug in your code or a bug in your math, probably both. So this was the state of machine learning back then. Maybe we'll come back to that. Great. So theory, drove practice. So I published this paper. I was working on conditional random fields. Then I worked on error bounds for sliding window classifiers. It was kind of a dead end theory, but that was my focus back then. So as a result, I didn't publish too many papers. So I have like 10 according to Google Scholar, but I have read a lot. And I have mostly worked as an engineer. So that gives you some context for my background. Even though I didn't publish much, I did a lot of research in the open source. So, one nice thing, there is internet nowadays. A lot of people are sitting online and they're just solving research problems for fun. So I've been active on, various forums. So in a sense, that's where most of my, productive research has been. Occasionally, I found collaborators on there. So on math, Stack Overflow, I, got to know a guy and then we wrote a paper together on finding how to find the best learning rate for a certain scenario. There's occasionally, respectable researchers thing out there. So this is a discussion where I discussed some things and then Peter Shor told me very nice computation. So that really made my day. That was like, I guess, meant more to me than, having a paper accepted. So that's the research side. Then, in reality, I actually did most of my work as an engineer. So I worked on finding, recognizing, real-time reading of runners' bibs. Because of that, I sort of ended up in Google because I was really into OCR. So I went to Google and I was like, I want to work on OCR. So I worked on this problem of detecting house numbers in street view imagery. That was around the time when Andrew Ng came to Google and he taught a course with Jeff Dean on, using convolutional or general neural networks. So I got really excited about it, and I ended up, working with Ian Goodfellow and Julian, to actually apply it to this problem. So that's like an example of a successful engineering effort where it would not have resulted in publication of a paper unless, Ian kind of wanted a paper. So it's like, okay, let's do a paper. But this is an example where it's useful to think about motivations. So me and Julian, we didn't have a motivation to publish. So we had a thing which just worked. And at Google, Google paid for engineers to go to conferences even without a paper. And, we got our promotions. So we didn't have any push to publish. So sometimes when you have engineers who are not motivated to publish and you see them publish anyway, that's a good signal that maybe the thing there works. So some more background. I worked at OpenAI with Tim Solomons on, squeezing larger networks into memory. We have this email thread with 91 messages called No Subject, where we ended up, collaborating. Right, so that's some engineering examples. And a problem as an engineer is that if you read papers, so you need ideas of things that work. So you end up reading papers, but often papers are misleading. So this is actually a very new example. So I worked at the company on Contextual on using this retro architecture, which was published by DeepMind. And one of the key figures in that paper was that it requires 25 times less parameters to reproduce the same log loss. So it sounds pretty promising, but we had a kind of a hard time. And some other people I talked to had a hard time reproducing retro. And I've actually ran into one of the authors on the retro paper, and he said, oh, yeah, it doesn't work. It's like, we tried an idea, it was promising, but it doesn't work. So we just published it and we moved on. You forget it like a terrible dream. The problem with that, you cannot tell this if you're actually looking at the paper. On the paper, it looks amazing, using 25 times less parameters. But as an outsider, you're like, as an outsider, you're like, this looks amazing. Let's do it. So there's follow-up. There's NVIDIA follow-up, which train large retro models, but their results are a lot less enticing. So that's a general problem with machine learning literature. So why does this problem happen? So I'm going to talk about a different field, which is much larger. There's about 10 times more papers published per year, and they've actually studied this paper of inflated results. So I will look at medicine. So in medicine, there is something like 1 million papers published per year, and people actually care much more when something doesn't work in medicine. In machine learning, if something doesn't work, you just waste somebody's time, but we have so much time nowadays. We have time to write all those useless papers. But in medicine, if something doesn't work and you publish it, you might mislead somebody, you can cause medical harm. So people have studied this problem, and there's been this paper in 2005, analyzing this, and you can see it's been cited 12,000 times. Now, a lot of those citations are actually people criticizing the paper, because with this paper, this guy essentially declared war on the entire medical establishment. These people are getting grants to produce findings which are true, and then this guy comes out and says, your guys' findings are false. So there's been a lot of criticism of this paper. Mostly the criticism center around, lack of evidence. So he says a lot of things like, well, it can be proven that they're false, but he doesn't actually prove it. So they're like, aha, hypocrite. However, some people, this paper is considered foundational because people have moved on and they actually try to look for evidence. So they actually try to look for specific example. Is it really true that most published medical papers are false? And the example that I like is people looking at gene association studies. So gene association studies is you're taking a particular gene variant and some disease, and you're saying, well, does one of them predict the other? And one example is this gene F5 and deep venous thrombosis, which is a very good prediction, but there's some associations which is a bad, bad association. And right, to summarize this, there's been 166 associations which were studied 3 or more times, and out of them, only 6 were actually useful in practice. So if we go back to our picture, there's things which are useful over here and things that are published. The intersection is only about 3.6%. And the thing about this is medicine. This is where they run hypothesis tests. They actually introduce some rigor in their testing. And this intersection is still very small. So the question is, what is it like for machine learning where we don't have this? And for this,
Yaroslav, can I ask a question?
Yeah.
I figured 20 minutes in, someone should ask some question just to get conversation.
Yeah.
So elements in the blue are published papers that are, if they're not also green, they're useless. Some of them are useless because they are like patently false. As in someone published an association that is not reproducible and like does not hold. Others are useless because although it does hold in theory and everything in the paper is correct, it just has no bearing on actual reality. In machine learning, how much do you think is kind of like the first set of things versus the second?
Yeah, I guess I'm restricting attention to applied machine learning. So applied machine learning are papers which are explicitly attempt to be practical. There is a separate thing, theoretical machine learning, which has no bearing to the stuff. So
okay.
I think, yeah.
So let's say even for just the applied papers, how many of them are useless because they are like the effect that they mention is literally not correct because they did not test it thoroughly enough, versus they measured some applied effect which could matter sometimes, but in practice it doesn't really matter.
I see. Yeah, so I guess I'm mostly focusing on papers which are making a specific claim. They're saying, hey, we have a method which works, but it doesn't work.
I see.
If they're making a claim, we discovered an interesting explanation, I consider that a theoretical paper. So here I'm looking at it as an engineer. Like you come in, you have a problem you want to solve, and you want to implement something that solves it. And if you take a random paper which claims it solves it, it does not solve it. And I want to estimate what is this probability of solving it? What is this 3%? Is it higher? Is it lower? You would expect it's lower because we don't do statistical testing, but there's actually a good example from this paper, which benchmarked a whole bunch of optimizers. So optimizers is a nice test bed because they're usually easy to implement. It can be just a couple of lines of code. So here they took 80 optimizers, and then they benchmarked on some data sets. So here we can look at the optimizers that they picked. So why did they pick those optimizers? So they picked the optimizer which sounded promising. So can you read the text, or should I zoom in?
Not much. I think you should zoom in.
Okay. Yeah, so basically they picked those 80 papers because they're applied papers which claim something is good. So, we have paper which found that significantly outperforms Atom. Or you have a paper which says they did extensive experiments and they demonstrated the efficacy and efficiency. You have claims like significant sample complexity reduction, which means that you need a lot less samples to train it. Then we have, this method which converges faster than state-of-the-art optimizers. Well, that's promising because they didn't compare with random optimizer. They picked state-of-the-art. Here's an interesting one. This method brings significant improvements, especially on complex networks such as DenseNet. So it already is pretty good, but then if you're using complex networks, it's really good. So that sounds promising. So here's a method where they just did a whole bunch of evaluations and they put it in the abstract. So it sounds like they're really thorough about their method. Here's a method which outperforms Atom in convergence speed. and it surpasses SGD in generalization. So it's like the best of both worlds. It's both faster and it generalizes better. Here is a claim which is especially useful if you pay attention. They bring about uniform gain in performances. So one issue with optimizers is sometimes it's easy to get an optimizer which is better on a specific task, but uniform gains means it's better on all tasks. If you have a classic optimizer which is uniformly better, it's definitely something that should be used. So this is a selection of optimizer they used. The question is how many of them actually beat Atom as they claimed. Well, they did a comparison, and it turned out that none of them uniformly beat Atom. So the lesson is that here the intersection of practical and useful is 0%. All right, some people, if you look at more experienced researchers, I didn't hide their names because they're doing something smart. They are not claiming that they're better. They're saying it can significantly improve the performance. So they're sort of hedging their bet. They have this optimizer, it can improve it. In medicine, it would never work. You cannot sell a pill. It's like, well, this pill can cure you. What does it mean can? Like 1% chance it'll cure you, 50% chance. But machine learning is not medicine, so we can do this. And presumably this paper got in with such weak claims is because maybe the writing was good, the idea was theoretically compelling, and it had Jeffrey Hinton and Jimmy Bai as authors. So perhaps those people can get their paper through publication process without inflated claims. Right, so that's obviously a problem. If we have 80 papers claiming that they beat Atom, but actually none of them beat Atom, that's disappointing, because how do you know what works? So I will talk now about why this happens. Why do we have such low rate of reproduction? Why do most things actually don't work if you do this? And when you have a paper which claims that something works, statistically significant, but it isn't, I will call it a research crime. And we want to know why these research crimes happen. And if you took this paper on about why most published research findings are false, there's 3 major factors which cause this. They're saying research finding is false to a high probability if there is a big flexibility in designing or defining your methods and outcomes. I will call this the weapon. The second factor which makes it false with high probability is if there is financial or other interests in demonstrating the result is true, and I call this the motive. And the final method or final factor they say contributes to things being unexpectedly false is if the scientific field is extremely hot, and then there's more scientific teams involved. And I will call this kind of problem accidental trampling. So now we'll go over in this three factors which cause this problem to happen. The problem of things appearing to be true according to publication, but in reality being false. So first of all, the weapon. What is this flexibility in design's definition? So going back to medicine, imagine you're trying to do a blood pressure drug, and then you're measuring how much it reduces blood pressure in millimeters. So normally the picture is you have some placebo, and then you have some point with some spread, and you want your measurement to be significantly different from placebo. So essentially you want there to be some kind of a gap, and this gap is measured by this p-value. P-value, it's sort of like negative log of the distance. So if you want this distance to be very high, you want the p-value to be very low. So essentially p-value of 0.05, it just means that you need to put a decent distance between your random measurements and what you're actually proposing. So suppose you're doing something and then your method, the p-value is actually very small. What can you do? So imagine you're doing a blood pressure drug. So you measure the improvement from some people, and then you actually conclude your data shows that it actually makes things worse. But then you're very convinced that this drug actually works. So what can you do? Well, you notice that, there's some, Bob and Jim, they're men, and you're saying, well, maybe the drug doesn't work on men, so you exclude them. And then now you get, a slight improvement, great, but the improvement is still not significant enough. And then you're looking, well, Alice is the problem, or maybe you subconsciously feel like Alice may be a problem. And then you're like, well, Alice is old, maybe my drug doesn't work on old women, so you exclude Alice as well. And then you're like, great, your improvement is 1.5, now it's statistically significant. So that's one way to make your non-working medicine or method look like it works, by choosing your data set, which you select on. The second example is, suppose you have this drug, and then you measured how much it reduces blood pressure, and then it did not reduce the blood pressure at all. But you actually, when you did the trial, you actually had people report their mood, and then you notice that people who took the drug are actually a lot less depressed. And then you're like, aha, well, maybe my drug doesn't work as a blood pressure medication, maybe it's an antidepressant. So maybe as an antidepressant is statistically significant. However, there is a problem with this. If you keep looking for an angle, eventually you will find some measure where your method looks good. And I had an example which I removed because I learned that the person thought I had beef with them. But roughly speaking, the example was, it was an optimizer, which it did not improve in accuracy, but it did improve in the variance of the estimates. So they essentially claimed that, well, we have an optimizer which is more consistent instead of having an optimizer which is faster. The problem is that if you're selecting your success criteria after the fact, it's a form of p-hacking. FDA does not allow the shenanigans. For FDA, you have to declare ahead of time. It's like, I'm going to try this method and I will check if it decreases blood pressure. And if you find that it improves depression after the fact, well, it's not statistically significant, so they don't allow it. On the other hand, in machine learning, you can do this because we don't have FDA. So the lesson is, if you see somebody report somewhat an unusual metric, you have to ask yourself, why are they reporting, variance or consistency instead of, something that's everybody else reporting.
Hey, Yaroslav, can we talk about another possible viewpoint here? So I absolutely agree that what you're saying happens. It happens in medicine, it happens in machine learning. You kind of like take a system, you play around with it, you collect a bunch of data, and then you look at the data many different ways. And then maybe one of the ways, 1 out of 20 is significant at the p.05 level, and then you try, then you publish it, right? On the other hand, like, how does one come up with the hypotheses in the first place, right? You come up with the hypotheses based on playing with data a lot, looking at 100 different ways. Then you see a way in which, there might be some effect here that nobody expected before. Maybe we should test this. So I would argue that actually science is this like loop process of playing with data, coming up with a hypothesis, stating it, designing an experiment to test that explicit hypothesis, testing it. If it works, publishing it, and going around in this loop. And what things like the FDA process do is they force people to state the hypothesis up front, which is one way of just like slowing down the speed of this loop and letting less things get into the testing phase. But I guess fundamentally, would you agree that in fact science is this loop, and it does require like making this plot, looking at this depression factor and realizing that might be a study worth running?
Yeah, in fact, that's how Viagra came about. They wanted to treat heart disease. They saw unexpected side effects, and then they made an extra study. And the thing is, you actually don't even need an extra study. So you could look at blood pressure and then find that it improves depression, and that could be valid as long as it's large enough. So Here, if it's slight, if you declare it ahead of time, it's enough to have this much distance. If you don't, you require this much distance. So you could actually find an antidepressant accidentally, provided it's large enough.
Yeah,
so
totally.
you just have to, yeah, if it's like slightly a little bit better, that's the problem with optimizers. A lot of them are a little bit better, and once you include those extra degrees of freedom, that's probably why they're not actually better. And the example, so another way this p-hacking works is, okay, so this is a more subtle one. So sometimes it's hard to see p-hacking because there's many ways of doing it. So one example is this distance that you need to clear. It depends on the spread in your placebo effect. So if you choose a data set which has high variance, then p-value, the distance to achieve p-value has to be very large. But instead of selecting the data of your control group, you can select the data of your placebo group. So for instance, if everybody in the placebo group had blood pressure exactly 120, then even a slight increase in your control group could make it statistically significant. And the reason I bring it up is, this p-hacking can be very subtle. It's not always easy to spot. So here's an example. You take your control group. If you have very little noise, then you don't need a large improvement to actually make it look significant. So in analogy with training, if everybody got like 75% accuracy on ImageNet, then 76 would be significant. But if people are like between 70 and 90, then you need 100% accuracy to be significant. A common, actually, going back to Jason's example, in psychology, there's this, well, let me jump here. There's this more common way where you come up with hypotheses by looking at the data. So they give an example in psychology departments. People may notice that, well, there's a lot of tall people and they appear to be Republicans. So you create a study where you take 20 people and you make the plots, and you do, say, oh, tall people are more likely to be Republicans. And the data. But with this p-hacking, there is a cool illustration of, let's see. Right. So the question is, this p-hacking, does it actually happen? And then there is an interesting paper which analyzes some p-values. So if you didn't have any p-hacking, you would expect the distribution of p-values to be exponential. There's a publication bias. You don't have, some papers don't accept things which are don't work, but some do. There's journals of negative results, but there's less of them, so you expect there's a drop of reported p-values. But if you actually look at the actual published p-values, there's an unexpected accumulation here. So there's actually a lot of p-values which are slightly below 5, 0.5. And that should look suspicious, because one way of obtaining this kind of accumulation is if you're sort of working with like p-hacking, looking at things, trying different things until you get to 0.5, and then you're like, I'm done. So that might be a phenomenon that explains this. That probably is the phenomenon that explains this. So the reason I bring this up is people are sort of tweaking things to make it look like things work, and they do it not just in machine learning, they do it in medicine. So let me tell you how this happens in machine learning. So what does the publication process look like? So first of all, there was an interesting experiment in 2014 where they looked at papers, and they looked at the probability of them being accepted or rejected, given that another set of reviewers accepted them. So basically, the experiment was to see how noisy is the process. Do only good papers get accepted or rejected, or do only bad papers get accepted or rejected? So the experiment was they send the same paper to two sets of reviewing committees, and then they see whether they were accepted or rejected by each one. So you can see if committee 1 accepted the paper, there's 50% chance that the committee 2 would accept it. And also, if out of the papers that were accepted by committee accepted by committee number 2. Whether paper is good or bad. If you have a good paper, you have a 50% chance of being accepted. If you have a bad paper, well, it has a 1 in 6% chance of being accepted by the other committee. So if you repeat this process 6 times, you get, 66% chance of being accepted. So this is what I call the submission carousel. So if you get a paper, if you're lucky and it's good, it might get accepted at the first conference, and maybe not, then it gets accepted at the second one, and you're done. But if you have a bad paper, in quotes, you will have to, repeat this carousel, maybe 6 times. The thing is, after submitting to the last conference of the year, you can resubmit to the same conference the next year because you'll probably get a different set of reviewers. So it may still get accepted. And if this is too hard, you can go to a different conference tracks with higher acceptance rates. So eventually you can get your paper in and then publish things. Any questions? Comments? Okay. Yeah, so the reason I bring this up is like that paper in medicine showed, things are more likely to be false when there's some motive for somebody to publish things that are false. So how do things get published? So imagine you're a grad student and a professor comes up to you and says, dearest grad student, here's an idea which will totally work. Let's write a paper. NIP's deadline is 3 months. So the student comes in and he tries it out, and the idea doesn't work. Now, what is the student to do? Well, if we go back here, the idea doesn't work. So clearly they don't have a good idea, so they're not on the short conference track, but they don't even have a bad paper, because even bad papers, they have to say something like, we have something that's interesting by saying it's significant, it outperforms something. So they're not on the good submission carousel, and they're not even on the bad submission carousel. They're not on the carousel at all. But they need those 3 to 5 papers to get their PhD. So what do? They can come back to their professor and saying, your idea doesn't work, but they're inexperienced, professor is experienced, it's awkward to do this. So instead, they're going to torture the data until the data shows that it works. You can torture the data by looking at different metrics you can measure. You can look at different data sets. So essentially, if you try things enough times, eventually you can find something where it looks like your idea works, and then you publish it. And then chances are that paper ends up in this big blue blob of ideas that exist but are not practical. So this is one motive idea. So there's this is especially why I don't trust papers from grad students, because grad students have to get their 3 to 5 papers to graduate, and most ideas don't work. Therefore, they have to make publish non-working ideas. But there's actually a second motive. You can actually see non-working ideas coming from senior researchers or people who don't have the publication pressure. And I will give you an example that's personal. So I have, at some point, I worked on this method called KFAC at OpenAI, and I got really into it. I'm like, okay, I got to make this work. I got to improve on it. I did some implementation, did some graphs. I got a graph where it looks like it works really well. It actually outperforms both Atom and SGD significantly, but to outperform it, I had to do this weird sort of task. It only works if you take a network with a very small bottleneck layer, but nobody uses them. But I'm like, well, this is an example that works. Surely I can fix it and make it work for other examples too. So I worked, spent a lot of hours in this unsuccessfully. At some point, I got in touch, started working with this group in Japan, where they had large-scale evaluations of this method, which appeared to work. And then I actually went to Japan and worked with this group. We packaged this method up. We had the poster at PyTorch. The reason I was doing this and publishing those things, I had a strong internal conviction. It's like, I know this method works. I just need to convince others that it works, and eventually I will make it work for real. But I know that it works, and that's sort of the motivation of the senior researchers. They have conviction, and you kind of need conviction to be able to keep going. But as a side effect, you end up, producing this publications, which may be a little misleading. So I did I'm actually sort of proud of the work I did on this. I came up with ways to improve it using this decompositions. The problem is it actually empirically didn't have any good results, so I didn't publish any of this work. But the question is, how were we able to, present this work as working in the first place? So to give a bit about K-fact, so imagine you're doing this minimizing a quadratic. You're essentially moving in this direction of the gradient. Oops. So you're doing this, you're doing this. So people notice that there's a lot of oscillations. So they're like, well, what is the best possible direction? You divide by this Hessian. So instead of moving in that direction, you're actually moving at exactly correct direction. Now, it turns out that this idea doesn't work in practice. So what do you do in practice? Well, you're saying, well, we need to regularize. So you essentially add this identity to your method, and then to actually make it look like it's not too much worse than SGD, you make this thing very large. And what happens when you make it very large? So here's an example of a random matrix, and then you add the large identity. Essentially, if you make this parameter very large, you're essentially making your method identical to gradient descent. So this is how this kind of method was able to get through publication in practice. You can make this parameter very large, and you make the learning rate very small in comparison, where you're at least as good as the previous method, which is SGD, and then you throw some extra things like some hyperparameter tuning, and then you demonstrate it becomes a little bit better. Okay, so now finally I will talk about the final cause of bad results, which I call death by trampling. So an example is, suppose you're tossing coins, and you have several people doing experiments, and things are around equal heads and tails. But eventually, if you keep tossing the coin, you're going to have a researcher which gets all tails, which is actually statistically significant, and you may get you may conclude that the coin appears to be unfair. The problem with this is it appears unfair for this researcher, but if you take all the researchers as a collective, it's actually expected to get these things. It's known as multiple comparison problems. And essentially, you're more likely to get this problem when, the field is hot. So you have to account for that. And for that, I will give a specific example. So there's this paper on grokking, which found some interesting things. So they looked at how if you keep training the neural network for a while, eventually it's sort of like groks. It's like, aha, I understand this. So they have this pattern, and then they're saying that we exhibit unusual generalization pattern. So what is unusual about this pattern? So first of all, you notice that they obtain 100% accuracy, training accuracy, but the testing accuracy still improves. So that part is not really unusual. So we've known, like in linear classifiers, you can get 100%, 100% training accuracy, but if you keep training, your linear classifier improves the margin. So things will improve even after you get 100% training accuracy. The thing which is unusual is this, the shape. It goes like whoop, goes like this. That's a little bit unusual. However, what is unusual to me is their choice of the y-axis. So you see they're using logarithmic scale. It's like 10, 100, 1,000. And whenever you see something unusual, you should always ask yourself, why does this happen? So we can ask, why do people choose unusual scales? So you can choose log-log scale because the behavior is a power law. It makes it look linear. You can use a log scale on the y-axis because it makes the exponential decay linear. But using log on the x-axis, I've never seen it before. So it's a little unusual. One reason it's unusual is if you take a statistic, like a standard, like logistic kind of curve, you're training a classifier and it converges towards accuracy 1, and you look at it on this scale, it actually looks like there is a sort of a jump. So that's kind of an unusual choice of axis. So regardless of whether this conclusion is correct or not, the point is that there was a flurry of research following this paper. So, I Googled searching for evidence for papers citing this one, and there's a lot of papers which are finding, emergent abilities, unifying grokking, and they're all finding extra evidence. So this is an example similar to our coin tossing example. So you came up with this hypothesis, it's like, hey, coin is unfair. And suddenly you have people studying it. I don't know how many people are studying it. Maybe there is 1 million researchers looking at this. If you have 1 million researchers, surely some of them will find some accidental evidence. So this is the problem. If I saw these papers before the grokking paper, I would be more inclined to believe them. But because the paper started this flurry of research interest, you have to be skeptical, whether this evidence is accidental or true. Another example is, in 2014, there is a paper from a famous lab on the attacking and identifying saddle point problem. And there was, more than 1,000 follow-up works. And basically what happened is first, there was a wave of papers which tried to capitalize it. So they would try to implement methods which actually, make this method practical. This method failed. So then there was a second wave of papers which are, trying to explain why this was not a problem in the first place. So you kind of have to be aware of these hype cycles. If you look at, in 2020, you look at all these papers, they look promising, but in retrospect, these papers came out because they were, trying to solve this problem, which later turned out to be not to be a problem. So you have to wonder, like, how many people were trying to solve it? How many of these results were accidental results? And finally, let me go over 2 other sort of research crimes. So the biggest research crime, the felony, is where you present something which works, but it doesn't work. There is a milder crime where you present something which works, but you may present it in a sort of misleading way. So I'll give an analogy of a stone soup. So a man comes into the village and it says, I can make a soup out of stone, and the villager says, you cannot do it, and he says, watch me. So he takes a bowl, puts a stone in it, and starts making his stone soup. And then at some point he says, oh, my stone soup is progressing fine, but I need a bit of salt. And the villagers say, fine, let's add some salt. And then he said, well, I need maybe some potatoes. And then they say, okay, add some potatoes. And then they say, well, I need more savory broth. And they add some meat. And in the end, you get stone soup, which actually tastes pretty good. So what is the problem with this? On one hand, you have something that obviously works. So it's not really a research felony. But the problem is you don't know why it works. Like, does it work because of the stone, or does it work because of other reasons? Maybe you could take the stone and replace it with a brick and it would still work. Or maybe you could just get rid of the stone at all, and it would still work. So I would call it a misdemeanor because it might be misleading. And the second example of a misdemeanor is a work, I would say work on this butterfly matrices. So there was work from the Stanford lab where they found that you could represent things like Fourier transforms using a combination of the special structured matrices, which is actually theoretically it's a very satisfying results. So they show a lot of nice properties. You have this universal way of constructing matrices, and you can recover arithmetic circuits. You could recover Fourier transforms. However, implementing it turned out to be hard. So eventually, the work they replaced these multiplication to make it actually work on GPUs. They replaced them with addition, and they're saying, well, if you squint really hard, meaning you look at the behavior around zero, addition is pretty much like multiplication. I don't agree. Like the properties don't really hold anymore. So in my opinion, it's an example where you take something that's like mathematically beautiful, but then to make it work, you have to kind of drift from this idea. So even though it appears in experiments that the method doesn't work too badly, it actually is not, it is not the structured representation because they replaced this multiplication with addition. All right, cool. I have 5 minutes. So what are the lessons here? So first lesson, sometimes path is long and things don't work, but you kind of have to persevere. So this is a slides taken from Alex Smola's tutorial on attention. Actually, attention had a pretty long path, and you had, all these intermediate steps until we came up with something that was transformative. But then if you look at any of these papers in isolation, they didn't appear to work. So sometimes it is necessary as a researcher to keep persisting on things that don't work. Even if they don't work, they do need to give some signal. So you have to pay attention to data. So it has to demonstrate some kind of improvement, even if it's a tiny one. And the lesson as a researcher and engineer is that the results are often inflated, and you have to sort of look at the motivation of people publishing it, sort of estimate what are the chances of it working. You have to be very skeptical. If you're actually an engineer that does research yourself, you have to be skeptical of yourself, because it is very easy to mislead yourself. You come up with an idea, you're confident it works. You have to always come back and look at the data and, trust data, don't trust yourself. All right, that's all I had for today.
Nice. How much longer can you stay after the hour, just so that I know?
I'm unlimited time.
Okay, cool. Then we can open it up for questions. Actually, let's stop recording for the Q&A so people maybe feel freer.